Recording in progress.
All right, let's go. This is our case. I have a sheet pile that penetrates the soil layer with 25 feet. In order to use the SEEP W, I need to make the geometry of the problem first. So I'm gonna put some coordinates here, 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 and these 2 points. So let's see, I'll assume this is my x-axis and my y-axis is this one. So the first point here is 0 and 0. Second point is 100 and 0. I assumed the length is 100. This point is 150. This point is 0 and 50. For these 2 points, the sheet pile is exactly at the middle of the problem. So the center of the sheet pile is at 50 feet. So for this point, the x-axis will be 50 minus 1, so it's 49. And the y value for that will be 25. And the other point, I said the sheet pile width is 2 feet. Then this point is going to be 50 plus 1, so 51 in the x-axis and 25 on the y-axis. The last 2 points, these 2 points here and here. So this point will have a coordinate of 51 and 50. This point will have 49 and 50. So these are the coordinates that I should define as points in the SEEP W program. So I can start defining my materials, my soil, my regions, and run the program to get the values of Q and then the contour lines that are required. So let's go to the program. So I'm gonna go to SEEP W now. Let me share my screen. GeoStudio, share. So for now, I'm using GeoStudio 2021, and let's make sure that we are on the student license, and then the template, the units are imperial and 2D geometry dimension, and then let's go for SEEP W. The pop-up screen that came out, let's rename our model and see. So I'm gonna write down here SEEP W analysis. My first case is only one soil layer, so it's a homogeneous case. And I will leave everything the same because these are some iterations and some units. So I'll close that. And then to define my geometry, I need to draw my axes first. So I'll go to sketch, axes, and then the elevation. I write down that it's just in feet, and then the distance is also in feet. I'll have on the x-axis, my minimum is 0, my maximum is 100. For the y-axis, the same thing. My max is 100, minimum is 0. And then I remove this auto increment size and close. So let's now define the points that I just drew. So define points. The first point was 0 and 0. Second point is 100 and 0. Third point is 150. Then 0 and 50. The points of the sheet pile, 4 points. The lower points are 49 and 25, 51, 25. The upper points are 49 and 50. the last point is 51 with 50. So now I defined the points, close that. So now you would go to draw the region. So draw regions, and then just move through these points. I'm gonna go through 1, 2, 3, 8, 6, 5, 7, 4, and then to 1 again. So, and then close. This is my region. Now I need to assign the soil that I have for this case. So define materials, add the soil name. I'm just gonna write down soil A, soil 1. For the hydraulic, the material model is saturated only, and then the value of the saturated X conductivity is given. It's 1.646 times 10 to the -4, -4. And then keep everything the same. Close that. And now assign your soil to the region that you have done before. So draw materials, make sure you select regions and then assign. I have only one soil layer here, which is soil A. I'm gonna go and then watch for the arrow. The arrow is now white. I'll go inside the region. It's black with a square. I'll just click and now my soil is assigned. Close that. The next step is to define the boundary conditions. So I'm gonna define them and then draw them on my problem. So define boundary conditions. Let's take those out and then add new hydraulic boundary condition. I'm gonna rename it as upstream, STRE, upstream. Colors red, kind. You have different kinds. I'll work with the pressure head, and then the pressure head from our problem was 42 feet above the ground surface. So 42 feet, and then I will add another one, new hydraulic, and then I'll call it downstream. And then I'll work again with pressure head, and then the downstream was at the ground surface, so it's skipped at 0. Then change the color to be blue, yellow, anything you'd like. I'll go with blue. Okay, close that. Now you would assign your boundary conditions. So draw boundary conditions, and then the way you select using lines, and then make sure that you assign upstream. The upstream was on the left side, so I'll come to the left side. My arrow is now white. When I go down to be close to a line, it will change to be black with a dash. Now I can assign the condition. So let's do the upstream, just click, and now let's select the downstream and then click on the right side. Close that. So now everything is defined. I'll just go and draw mesh properties, and then I'm only allowed 500 elements in the student license. I'll try to minimize my element size to get close to the 500 elements. So let's go with 3 feet element size. Okay, now I exceeded the 500 element limit. So let's see, 3 feet gives me 560 elements. So I'll increase to 3.3 and see what will happen. Okay, 3.3, I have 476. I'll go to 3.2. 3.2 also exceeded the limit, so I'll go with 3.25. 3.25 element size, have 488 elements, and I guess this is the maximum elements I can get. So I'm gonna close this view mesh. So now my problem is ready to run the analysis. I'll just go to the solve manager here and then start. Save. So I'm gonna down homogeneous soil trial 1. Save. Now this is the solution. I'll just remove those vectors. I think it's from here. Oh no, this is to draw. So if you want like to hide the vectors, it's on this right panel here, view vectors or hide them. Now I'd like to show the contour lines of the total head. So I'll go to draw contours and then select the total head. It's already drawn now. I'll close that. I'll just draw the flow paths or the flow lines. So draw flow paths and then just click on the screen in the solution range here. Anywhere it will draw flow line. I just have 3 for now. Let's label the contour lines. So draw contour labels and then click on the contour line itself. You will see that the labels coming. So those are the labels for the contour lines of the total head. The next graph that you would like to show is the gradient graph. The gradient graph follow the same procedure, draw contours, and then the gradient is not here. So you're gonna add it. So add, and then name gradient. And then the category is the flow category, water flow, and then the parameter is XY gradient. And now I'll uncheck this auto arrange and I will use a small increment of 0.05 and I will increase the contour line numbers to be 20 instead of 11. Close that. I will hide the flow paths from here. So those are my contour lines for the gradient. I will also label them. So draw contour labels. And here, just pick a couple of them and it should be fine. So those are the labels for the contour lines in this case. Now I'd like to show how you would calculate the amount of seepage or flow. So you will go to draw and then graph and then add, we'll call it here flux or flow or seepage, anything you'd like to call. Kind mesh, and then the category is flow, and then it's the rate versus the time. And make sure you check this box here, the sum of the values. So I'll check this box and then set locations. I'll draw a cross section to calculate the value of seepage through that section. So use subdomain cross section, and then I will make a line from down here from the impervious soil layer till the end of the sheet pile here. Right click to get rid of this line and then show graph. Let's maximize this. If you can see, this is my point. And then the value is already written here as 0.00303, and the unit is in cubic feet per second. And the last thing to show is the exit gradient. If you'd like to show the exit gradient, there are 2 ways to do that. One way using the graph as we are now. So I'll go with add. I'll name this as gradient mesh. The category is flow again. And then instead of rate, use XY gradient. And then keep this box unchecked. And again, the gradient is also versus time, not distance. And for the location, I will show you all the downstream line, set locations, and then get close to the downstream line here, and you will see that, okay, this is the black arrow with the dash. So select that and then show graph. And then you will see this, all these dots. I know it's tiny dots. Maybe it's something related to my laptop. So these tiny dots, all of them have the all gradients for all elements on the downstream line. let's say you would like to show one specific element. So set locations again, and then keep it on subdomain and locations, and then use subdomain, use custom subdomain. To select a specific element, you can select that from the right corner of it. So let's say I would like to use this element, the second one from the sheet pile here on the right side. So I'll click on the right corner here. So now this element is selected. Show graph. This is the point of the exit gradient. It's close to 0.496, and it's between 0.496 and 0.498, but it's not 0.497. Due to this, you can, because you cannot read from here, you can use the other method. I'll close this. And then to show it easily, you can go to view and then result information, and then select any element you would like. Let's say I'll select the same element. I'll just go here and then select it, and all the information you will need is there. Go for the XY gradient. It's here. The exit gradient is 0.4844. You can use the exit gradient to help you calculate the factor of safety. You know that the factor of safety is the I critical divided by the I exit. You can get the I critical, and then the I exit is 0.48. So this is what you would do for this case, the homogeneous case. What you would do that is different from the homogeneous case in the two soil layer case. I will unlock my solution by clicking on the definition. And then I will go to this model that I made, right click, and then add analysis, and then clone, and then analysis. Now I have a copy of my geometry of the problem, and then I'll just rename that. And instead of homogeneous, I will write down non-homogeneous. So non-homogeneous. And then I'll change the material. I will add one more. I will change the regions in order to have the proper geometry of the problem. So let me hide the mesh and then define regions. I will delete this region, delete. So now I have nothing except for the points. So my points now need two more points. I need to add 1 point here on the right side, with 1 point also on the left side. These 2 points are on the line that passes through points 5 and 6. So if I extend the line 5 and 6 to the very right, I will have 1 point here. The point coordinates will be 125. And the same thing if I do it with the very left, the point coordinates will be 0 and 25. So let me define points, add the first point. I said 100 on the X and 25 on the Y. And then the other point is 0 on the X and 25 on the Y. And then I added now these 2 more points. So let me close this. And now my regions will be defined as follows. Regions, I'll go through one. Oh, not from define, my bad, I'm sorry. Draw regions 1, 2, 9, and go all the way to 10, and then 1 again. So this is the first region. The second region is 6, 9, 3, 8, 6 again. And the last one is 10, 5, 7, 4, and then 10 again. So those are my regions. Now I need to add one more soil layer, which will be the lower soil layer. So define materials, add soil B, and then I'll use saturated only, and the value of K, let me see what was the value of K. The value of K is 8.2 times 10 to the -5th, -5. And then click close. Now I will assign my soil layers. So draw materials, soil A, the upper soil, and then soil B, the lower soil. Close that. I need to reassign the boundary conditions because once I deleted the previous region, everything that was assigned got deleted. So let's draw boundary conditions, and then upstream on the left side, and then downstream on the right side. Close that. Let's double check the mesh. So draw mesh properties, and then 3.25. I have still 488 elements, so I'm okay with that. So let's run the test. Start. But before we start, I will deselect the homogeneous case from here and then run. So now this is my contour lines for the second case, which has the two soil layers. Let's see what we will do here. We'll do the same thing we did for the first case, contour lines for flow lines with total head. So this is the total head contour lines. I'll just view the flow paths from here. Those are the three flow lines that I did before. So I will hide them again and show the gradient contour lines. So this is the gradient, as you can see. And then same thing, we need to calculate the value of Q. So I'll go to draw graph. I will go to flux, and I will just, so as you can see, it's already there, 0.00216, but let's double check the cross section and double check everything. So flux, flow, category, rate versus time, and then the box is checked. Set locations, the line is already there. So show graph, it's the value that we are looking for. And the unit is in cubic feet per second. So let's close that and go for the exit gradient. So view result information, and then pick your specific or desired element. So let's see this one. So this one here has an exit gradient of 0.374. Let's try another one here. So this one has an exit gradient of 0.39. And you would choose the element that gives you the highest exit gradient, because the highest exit gradient will give you the lowest value for the factor of safety. And that's it for this assignment. And thank you.